Hi, my name is Muhammad Shamsul Hamizan bin Muhammad Nasuha. So today I will talk about the introduction of energy absorbable lamellar structure of soap bubble. What is lamellar structure? Lamellar structure, also known as microstructure, are made up of tiny alternating layers of various material. They are common in situations where a phase transformation front moves swiftly, leaving two solid products behind, such as when eutectic or eutectoid system move quickly. The soap bubble structure found in nature has been an inspiration to have applications in the field of architecture, transportation, mechanical engineering, aerospace, chemical engineering, biomedicine, and many more. In soap bubble, growth is achieved through a system of division and inflation. This increased internal pressure encased in a reinforced membrane subject to tensile stress causes the bubble to grow in process known as isomorphism or self-generation. The free-floating bubbles collide and form dense cluster known as foam. If three bubbles are placed on a glass surface and a fourth is added, the fourth bubble will relocate to the top of the three bubbles to form the simple 3D cluster consisting of four bubbles. If further bubbles are added, they will automatically form a foam structure. If the bubbles are of equal size, the liquid edges of the foam are straight and of equal length, and the angle of incidence at the nodal point are equal. The total structure forms a net of equal mesh size called the basic net. The structure are formed through the solidification of a 2D bubble cluster. Bubble cluster occur when bubbles are freely dispersed within a cell without touching each other. In the next phase, the bubbles are introduced to each other through point of contact and form pattern by agglomeration. The patterns are based on geometric forms such as cube, tetrahedron, and octahedron. As solidification takes place, the membrane of the bubbles dries out and the fiber net hardens. The bubble membrane then dissipates and the net structure is left. These are the picture about configuration of soap bubbles. In this study, we propose a novel structure for soap bubbles. There is a comparison of elastic properties for soap bubbles, novel designs, and hybrid structure. The deformation mechanism is used to evaluate the building of novel designs and hybrid structures. The elastic characteristics of design structure are determined via a finite element analysis. The samples generated utilizing experimental in ANSYS software validate the result of the finite element investigation. The results of the modeling are in a good agreement with those of the experiment.
Methodology. The biomechanical design process, usually using the biomechanical design spiral developed by the Carl Hestrich in 2005. The biomechanical design spiral provides a succinct description of the essential element of this design process that uses nature a guide for creating a solution. Each describes the six most important phases is identify, second translate, observe, abstract, apply, and evaluate. We follow all these steps to find the best one design that we want to use. Design of soap bubble, we want to choose the best one from these three design. The three design is of soap bubble is two configuration of soap bubble, four configuration of soap bubble, and six configuration of soap bubble.
Hi, my name is Siti Nisa. I will explain about simulation and result. For simulation, we use ANSYS to do the simulation. First thing first, we must select the material. We select structure steel as our material. It has tensile ultimate strength is 460 megapascal. And then we import the design into the ANSYS. And then we apply mesh, apply load at the y direction at the upper of the design, and fit support at the bottom of the design. We solve the design and find the equivalent stress answers for the design, which is 2 bubble as you can see in the table, 4 bubble and 6 bubble. We choose the suitable load for our material and design by using try and error. Maximum stress must less than tensile ultimate strength of the material, which is 460 megapascal. After try and error, we got 2 megapascal pressure as our load. After that, we choose a node at the same location for each design, and then we compare the stress, strain and deformation. As you can see here, the result of the table for each node. We convert the result to the graph. As you can see here, we have graph stress, strain, deformation for each design.
Hi, I'm Ain and I will be explaining about cost versus efficacy. From the table, we can see that the cost increase as the number of soap bubbles in the design increase. Since the higher the number of bubble per design, its volume and weight also will be higher. Out of the 3 soap bubble design, the 2 bubbles design is chosen as its maximum stress is below 276 megapascal and substantially less expensive but effective. A992 steel cannot be used for this design since its tensile strength is lower than the analysis tensile strength. After the analysis and comparison is made, A36 steel grade is chosen as the material. Although it has the highest price out of the 3 material, it is still considered low compared to other materials such as stainless steel. A36 also is widely used as construction steel, so there is almost no risk in the future, hence making it cost efficient in long time run. For TRIZ matrix, 2 parameters each are chosen for improving feature and to preserve feature. For improving parameter, the feature chosen are the weight of stationary and strength, while for to preserve parameter, the feature are stress and stability. Using the TRIZ matrix, there are 4 solutions chosen. Firstly is local quality, where protective coatings such as hot dip galvanizing and thermal spraying should be used to improve the strength. Next is preliminary action, where the building should apply prefabricated construction as it improves the strength and quality and also save time and cost. Next solution is parameter change, where the mechanical joining method should be changed to structural adhesive as it can maintain strength over a wide range of temperature. Lastly is inert atmosphere, where an optimal condition is created.
Hi, my name is Feren Kancina Balai, and today I would like to present on the properties of design for our bubble soap biomimicry. From the table, we can see that the volume and weight increase as the bubble of the soap biomimicry increases, which this means that less volume and weight much better compared to the high volume and weight. So the first design, which is 2 bubbles, will be validated by the engineer since it has low volume and weight. Hence, the engineer will be able to save cost in terms of the cost of the material. The next part is the analysis of result. From the table, the first design is 2 bubbles with a spherical shapes. Since it is spherical shapes, it has the highest arc strength, which means it is very stable, efficient, capable of larger spans, and can withstand larger load. While for 4 bubbles, we can see from the table, it's already have sharp edges, thus it is easier to fail and not safe to be used. For 6 bubbles, the bubbles have different shapes, so the stress distributions is dispersed to different branches in the bubble wall, so the maximum burden is small, which this result to the lowest maximum stress. Thus, our group are all agreed to choose 2 bubbles as our main design as it is the strongest one and it can also achieve the lowest manufacturing cost as it have the lowest volume and weight. In terms of materials, we compare 3 materials from structural steel, which are ASTM A992, ASTM A36, and ASTM A242. From the table, the ASTM A992 is not valid to use since the value of the tensile strength is 450 MPa is lower than the actual tensile strength for 60 MPa. Hence, it's easy to fail and not safe. In comparison, ASTM A36 and ASTM A242 are much better than ASTM A992 since they have a higher tensile strength. Our team decided to use ASTM A36 as we need to consider cost of the material since it has an affordable price.
Alright, thank you. So for further analysis, you can see that in graph 1, design of nodes in two bubbles have the highest equivalent stress, which means it have the highest allowable stress to withstand the load. It is same goes to graph 2 that show two bubbles have the highest equivalent elastic strength, which means it have the highest maximum deformation. Next, for graph 3, it is shown that the data is fluctuated since the total deformation for four bubbles is the highest one. The reason of this analysis is actually because of the shape of two bubbles was in circle, thus it have the highest arc strength, which means it is very stable, efficient, capable of larger span, and can stand a bigger load. Thus, our group will agree to choose two bubbles as it is the strongest one and it can achieve the lowest manufacturing cost. Next, in terms of materials, we choose the STM-A36, but there is some recommendation for improvement on this material since it have the lowest yield strength. When yield strength is lower, the elastic behavior is lower because the allowable load is very low, thus it is easier to fail. So in order to improve this design, we need to choose the STM-A242 since it have a higher yield strength and the cost is cheaper than the STM-A36. Finally, our design is also safe since the safety factor is 1.96, which is lower than the safety factor for structural steel, which is 4. That's all from me. Thank you.